Examples. Okay. Many of the standard stuffs will be separable, but we'll also see some non-separable stuff. Let us look at, first of all, if we take R with the usual metric, whenever from now on R usual metric means dxy is equal to absolute value of x minus y, that is the usual metric, is separable since the rational numbers are dense and are also countably infinite, is a countable dense setting. So that is the first example, the real line. Real line has most of these nice properties. When you generalize, some places lose them, some places don't have. That's the first example. The second example, let us take the complex number. So omega to be C. This is a collection of all complex numbers. Again, we define the metric as, or if you want to use complex notation, xy always somehow means real. I don't know why. These are W to be mod z minus. It looks impressive. Is other than x. So dz minus W is mod z minus W. This is a metric, we all know that, very easy to verify. Triangle inequality is satisfied, etc. And so CD is the metric space. I will call this the usual matrix for the complex numbers. This matrix I will call as the usual matrix, just like we call this absolute as the usual matrix. Now we claim this is also a separable matrix space. Now I will do one or two or three of these examples, point out some of the details, because you will realize the importance of this construction and this rational numbers in the context. Now what we want to show is what? First of all, we have to get hold of a dense set and we have to get hold of a countable infinite tensor. So let's take any number z in C, implies z is of the form x plus iy, xy being any complex number can be written in this form, x plus iy, where x and y are real. Now, for every epsilon, I can approximate, let's say epsilon 1, but I will adjust the epsilon 1 later. Given any error and any real number, in particular the real number x, I can approximate this by a rational number, I can approximate this by a rational number. So there exists q1, q2 belonging to q such that mod x minus q1 is less than epsilon 1, absolute x minus q2 is less than epsilon. Each one of these I will approximate it within that error. Now I will construct the complex number that is, not q squared, anticipate. C, this is a complex number, and what is mod z minus q? I will call this as q. This is square root of x minus q1 squared plus y minus q2 squared. But x minus q1 squared is less than epsilon 1, x minus y minus q2 is less than epsilon 1, so this will be less than square root of 2 epsilon 1 squared. So all I have to do is choose the epsilon 1 such that square root of 2 epsilon 1 squared is epsilon. So 2 epsilon 1 squared to be chosen as epsilon squared, or you choose epsilon 1 by as square root of epsilon by square root of 2. So I will start like this, so epsilon by 2. Now I know. Then this will say for every epsilon positive there exists q in C, q1, q2 belonging to q such that mod z minus q is less than epsilon. So therefore what this says is any complex number can be approximated within any error by complex numbers whose real and imaginary parts are rational. So therefore we will call this as CQ. So let S be CQ. The set of all Q in C such that Q equal to Q1 plus IQ2, Q1, Q2 belonging to. So looking at complex numbers whose real and imaginary parts are rational. Then for every x z in C, for every epsilon greater than 0, there exists Q in CQ or Q in S such that mod z minus Q is less than from here. Therefore S is X. Now we want to show that that's also countable. It's obviously countable infinite. If you look at the points in the plane, the Argand diagram, they occupy the points in the plane with the rational coordinates. So we see that CQ is equivalent to the set Q squared. Every complex number of the form gives might be a vector in 2 dimensions Q and Q2 with rational coordinates. But Q2 is countably infinite. Therefore CQ is countable. So therefore S is a countably infinite dense subset. C, therefore C is separable with this metric. Okay? You must remember that in all this discussion the metrics plays the role. We are approximating with respect to that distance concept. So with this metric the complex numbers form a separable matrix. Now I am going to make a slightly move towards the higher dimensional spaces, the so-called higher dimensional spaces. Let us look at, just to illustrate, actually we have moved to the higher dimensional spaces here itself. The C can be thought of as the 2-dimensional plane. So actually we have done R2, C is R2, and we have shown that the Q cross Q is dense in R cross R. That's what it is. And the distance is the Euclidean distance, that is square root of the difference in the coordinates squared. So basically the complex numbers are identified in the plane and everything is there. So in general, suppose we look at what does this mean? This means, first of all, consists of vectors x is equal to x1, x2, xn, n component vectors with each component belonging to R. So this n and the R says I have n components and all the components are real numbers. That is the first. What is that P saying? That tells what is the distance the distance between two such vectors is defined to be the difference in the coordinates p power, add all of them and take the 1 over. I am looking at 1 less than equal to p less than infinity, because for that is a satisfies the triangular inequality, which I have not proved, but we will come to that shortly, proving the triangle. So this is the distance. Now our claim is the following. In 2 dimensions, at least with the Euclidean distance, the vectors with rational components form a dense set. Now we try the same idea here. Here again we will show that the vectors with the rational components and rational components will still form a dense set. It will follow the same idea here. So let, what shall I call, omega q be the set of all vectors x in L, P and R. X is equal to x1, q1, q2, qn, qj. So let's call it as q. So you collect all the n component vectors whose components are all rational numbers. So these are all rational coordinated points. Now we will show, first of all, omega q is isomorphic to qn, set theoretically, is equivalent to qn. It's in fact qn. So therefore what does that mean? Omega q is in fact, therefore omega q is countably. So omega q is countably infinite. Because if you take a countably infinite set and Cartesian product any finite number of times, it is still countably infinite. Now we show that this is also dense. What is the idea? The idea is the same as before. There we have 2 components x, y, here we have n components. What did we do? We started with an epsilon and then approximated everything by epsilon by root 2, so that the sum will become. Now what should be approximated with? Instead of 2 components we have n components, instead of the square root we have the pth root. So that's all we are going to do. So given any epsilon positive, any x in LPN, okay, choose epsilon 1 is equal to epsilon by n to the power of 1 over p. This is an error which is positive, because epsilon is positive, n is positive. So each xj being in R can be approximated by a qj in q such that absolute value of xj minus qj is less than epsilon 1, which is epsilon by n to the power of 1 over p. Right? Therefore, this implies, so let q be the vector q1, q2, qn. Where does this belong? Because it has all rational components, it belongs to omega q. Also, what is the distance between x and q? By definition, the distance is the difference in the coordinates p power 1 over p power. So it should be j equal to 1 to n xj minus qj to the power of p to the power of 1 over p. Each one of them is less than epsilon by n to the 1 over p. There are n terms, the total will be, the peak power will be less than epsilon p by n, n of them, so it will be epsilon power p, so it will be to the power of 1 over p. So what we have shown therefore is given any vector x, given any hierarchy epsilon, we can find a q in omega q. Therefore, for every x in omega, what is it, LP n r, for every epsilon positive, there exists q in omega q such that txq. That is, that ball contains the, therefore, omega q is dense. So it was already countably infinite. So it has a countably infinite dense subset, and hence all these are. So therefore omega q forms a countably infinite subset. Therefore LP and Q are these separable. These are all very standard examples. Okay. And most of the time you work with one of these. If you have discrete finite, it is LPM. If it is a discrete infinite number, it is LP. And if it is a continuum, it is this function space LP. These are the standard spaces in which you will be working with. Or some very crazily constructed, concocted subspaces of these fellows, which will carry all kinds of funny names based on which fellow you invented. Okay. All these L's stand in honor of Lebesgue. Little l is small, small l doesn't mean small Lebesgue, and big L means big Lebesgue. These are all simpler spaces. These are discrete. The capital L is a little more involved. That is why. All right. Alright, so what about L infinity? This is example 4. What is L infinity n r? This is the set of all vectors, again, with n components, real numbers. So this always says how many components, this says where are the components from. Okay. And this is the one that tells what the metric is. What is the metric here? It is the maximum of the difference in powers. It is the maximum of the difference. Now it's very easy to see that this is still the dense set, because now I have to, all I have to do is I approximate each coordinate within epsilon. So the maximum will also be within epsilon, and we are done. Okay. Again, let omega q as before. Then given x in L infinity n r and epsilon positive, approximate, can find qj in q such that absolute value of xj minus qj is less than epsilon. Any real number can be approximated by a rational number within any accuracy you want. Now I am using the accuracy qj, epsilon itself. Then q equal to q1, q2, qn belongs to omega q, and what is dxq? It is the maximum of the difference. Each one of the difference is less than epsilon, so the maximum will also be less than epsilon. Therefore, for fx in L infinity n r, for every epsilon positive, not empty, therefore omega is dense. Is again as before, countably infinite, and therefore L infinity and countably. Therefore L infinity n r is separable. Okay, so these are you take in the finite dimensional space with any one of the standard metrics, it is separable, and one standard countable infinite dense subset is always q power n. They make all rational coordinates and collect all those coefficients. That will always work out as a countably infinite dense subset. Okay. Now in all these proofs you see that the crucial thing we did was each coordinate can be approximated by rational numbers within any degree of accuracy you want. That's the main thing. So basically what is it? Doing n dimension was more or less doing one dimension n times, and do it cleverly. Do each coordinate approximation properly, then you have got to put them on the ensemble can be put together and you get the correct approximation overall. Now, that wouldn't have affected even if I had taken complex numbers here as coordinates. Because previously we said any complex number can be approximated by a complex number with rational coordinates, and that will become a countable dense subset. So similarly, I will write therefore, similarly,
LPNC and L infinity and C are also separable dimensions.
so all these finite dimensional spaces, the finite dimensional vector space, real or complex finite dimensional vector space, with any of these usual metrics, standard metric, is always a separable metric space, and the vectors with the rational coordinates give us the countably dense subset. This is hereditarily coming because every real number can be approximated by rational numbers, and the vector is formed only with real numbers, and therefore that approximation also goes on carrying over coordinate wise, and we get the result. Now I get to one step little more. Suppose instead of finite number of coordinates, I get a countably infinite number of coordinates, infinite number of coordinates. So next I will investigate what is this example 5. Don't worry about number, it is n plus 1. LP R. Now again, if I do R, the same thing will work for C also. What does I mean by LP R? I have dropped that n. That means the number of coordinates is infinite, it goes on. There is no limit for the coordinates. So I have these vectors. I will leave some space. What should be the metric? But all kinds of convergence problems arise. Okay. Well, I don't know whether the series converges. Suppose I want to take the distance of the vector x from the y vector, 0 vector, then I must have this as the distance mod xj to the power of p. But I don't know whether that series converges. So if it doesn't, I put it as hypothesis. So what is hypothesis in the theorem means? Whatever you can't handle is hypothesis. You put it as a hypothesis. It suppose that means such that summation j equal to 1 to infinity mod xj to the power of p 1 over p. Well, if 1 over p is less than infinity, that also is less than infinity. So, if that is so, then this becomes a metric. It's not easy yet. To prove the triangular inequality is not easy, but we will prove the triangular inequality once and for all these inequalities sometime. So let us take it for granted that this satisfies the triangular inequality. Also, other things are easy to see that it's a metric. It is non-negative. It is equal to 0 if only if xj equal to yj. Those two vectors, and it is symmetric. The only non-trivial thing in all these things is the triangular inequality to be verified, and that we will see at one stage sometime. Now let's grant that this is the metric space, and then let us see whether we have a dense subset. Now let us see whether we can copy what we did in finite dimensional space. See, this is where Many things that you do in finite dimensional space you can copy in infinite dimensional space, but every now and then there is some stumbling block because you have infinite number of coordinates. You have to handle them carefully. Now let us see what I would do. How did I construct a dense subset here? I took all vectors with rational coordinates. So I would have taken, if I had to copy that, I would have taken rational coordinate vectors here, infinite number of them. But then what would I do? Each coordinate can be approximated by this. There itself I am stuck because it is n to the power of 1 over p, but my n is now infinity and that creates problems. So I cannot copy that idea at all. There is going to be a difficulty in approximating every coordinate and putting them all together. When you put them all together, it just may happen it is too big, the error is too big. So how do I handle this? There are many ways. We will do it in a simpler way. First of all, the idea is, I am okay if I have finite number of components, right? I can do all this. Therefore, what I will do is I will reduce the problem to a problem of finite number of components. That's the idea. The idea is, how do I reduce it? Where was I? Which is my page? This one. Okay. The idea is, what we will do is, first give me any vector in LPR. I will approximate by a vector which has only a finite number of non-zero coordinates. In all the other coordinates beyond a certain stage 0. And once I approximate this fellow now by rational coordinates because I have only a finite number of them. That is the idea. So how do we do this? First of all, let us say we are given any x in LP and any error. This is how we start. We see whether the approximations can be done. So give me any vector and give me any error, epsilon positive. Then we have summation j equal to 1 to infinity mod xj to the power of p is less than infinity. That's given to us. That means, what is meant by a series converges? A series converges if the tail can be made as small as possible. That's what it really means. So therefore, given any epsilon 1 positive, therefore, for every epsilon 1 positive, there exists an n1 such that if you look at the terms of the series beyond that stage, they all add up to something less than epsilon 1. That's all. The tail part can be made as small as possible. That is what is meant by convergence of an infinite series. Now, what does that mean? Look at x tilde, which is x1, x2, xn1. It coincides with the given vector up to the first n1 coordinates, then becomes 0. All the other coordinates are 0. Right? Now, what is the distance between x and x then?
Less than epsilon.
It is summation j equal to n1 plus 1 infinity mod xj to the power of p to the power of 1 over p. Right. Therefore, what this says is, why is this? Because the first n1 coordinates were the same. Therefore, the difference is 0. Beyond the n1 coordinate, these coordinates are all 0. The only thing that survive are the coordinates of x. But now this is less than epsilon 1 and therefore this will be less than epsilon 1 to the power of p. Is it epsilon 1 to the power of
1 by
1 by p? So what should I choose epsilon 1 as? Don't worry still. Okay. Don't worry still. Let us keep it as epsilon 1 power to the power of 1 over p, because we have not completed our approximations yet. Keep it floating. We will choose the epsilon 1 later depending on epsilon. So given the epsilon, choose the epsilon 1 to be this and then do all these things. You will get the correct answer. Okay. Now, we may be tempted to think, I have already done, all I have to do is, I have to take all vectors which have only a finite number of non-zero coordinates and they form a dense set, because anybody in the space can be approximated by vectors with finite number of non-zero coordinates. But however, the collection of all vectors with finite number of non-zero coordinates forms an uncountably in the space. So that's not good enough to form the separability. Having reached that state, that we will replace by finite number of rational coordinates. Okay. Now, exact so given epsilon 2 positive, I don't know what error I am going to choose. I will decide on the approximation that I want later. There exists q1, q2, qn1 belonging to q such that mod xj minus qj is less than epsilon 2. That I can do. And therefore, if I now let the vector q tilde to be the vector q1, q2, qn1 and then let it 0, 0, 0, 0, then what is the distance between x tilde and q tilde? That is equal to summation mod xj minus qj to the power of p to the power of 1 over p only from 1 to n1. What is that equal to? Less than? Each one of them is less than epsilon 2 to the power of p is that correct?
N1.
N1. Just N1 epsilon 2. Okay, it is just N1 epsilon.
1 by p.
N1,
Or 1 by p.
okay, there's a 1 by p. Epsilon. That's how I choose the 1 over p. That's exactly what the approximations we did. Okay. So now therefore, what have we got? What is the distance between now x and q hat? By triangle inequality, this is less than or equal to the distance between x and q plus q hat, x and x hat plus x hat to q hat. If you want to go from x to q hat, you go to x to x hat and then to q hat, that distance will be small. So therefore, now what do I know about this? That was something somewhere here. Epsilon 1 to the power of 1 over p. And this was epsilon 2. Now if I make this as an epsilon by 2 and this an epsilon by 2, the total will be less than epsilon. So now I know, choose epsilon 1 such that epsilon 1 to the power of 1 over p is epsilon by 2, epsilon 2 such that epsilon 2 to the power of n to the power of 1 over p is epsilon. Then this is less than epsilon. So given an epsilon, choose that epsilon 1 and do this, because I can do it for every epsilon 1. So choose that epsilon 1 and get your x hat, and choose this epsilon 2 and get your q hat. So you have got an approximation of q hat, x by q hat within this error epsilon. So therefore, now I take the set of all vectors with finite number of rational components, and that is countable. Why? Let's exercise. Okay, that's exercise the first part of the lecture. Now let omega q be the set of all vectors in LPR which have only finite number of non-zero coordinates, each of which is a then omega is dense, countable, therefore LPR is yeah. Okay, and no problem if I replace R by C. The same things we can do again. Instead of now each component, the real part and imaginary part has to be approximated by rational numbers. And omega q would be set of all vectors in L2R which have only finite number of non-zero complex, but here it will be non-zero real, non-zero complex coordinate. The real and imaginary parts of each of which is a rational number. So that's how it comes. So similarly, so I'll write here, similarly, L to C, LPC, 1 less than B is so we are moving fairly well now. Almost all these component vectors, sequences are finite. The only thing left is L infinity. That L infinity R is the next example. Where are we? What is the example number? Forget about it. Example L infinity R. What does this consist of? This always says coordinates. Now here is where the problem is. What is, I'll leave some space. I have to define the distance to be the supremum of mod xj, least upper bound of this. Difference in the coordinates and look at the difference. But then, even if you want to look at the distance between x and 0, I will have to take the supremum of mod xj. To make sure that the least upper bound exists, I must make sure that it is bounded. So I must consider only bounded sequences. This mod xj, bounded sequence. So we take the set of all bounded sequences and then consider this distance, and this is a metric. And in this metric space, you cannot now carry over the arguments. You are in trouble. Turns out this space is not separable. This is a claim. This is one of the examples of non-separable spaces. Now, whenever you want to show something is non-separable, the trick is to show that there are a large number of fellows sitting far away from each other. They don't want to come close to each other. In other words, if I show that there are an uncountable number of fellows sitting such that the distance between any two of them is 1, say. or half or k, fixed k, then to approximate each one of those fellows, I need at least one fellow from the dense set. So there will be as many fellows in the dense set as there are these points. And if these are uncountable, dense set must be uncountable. The way to show this is, show this by showing that any dense set is uncountable. This is a typical way of showing that something is non-separable. If we show that any dense set must be uncountable, there is no hope of getting an countable dense set. You have to sacrifice either density or you have to sacrifice uncountability. If you want density, you must have uncountable. So there is no question of having density and countability together. So that is the way to show that something is not separable. Now how do we do this? The way generally to do this is manufacture a subset X of the metric space. So this is generally any metric space we want to show it's non-separable, this is the way to do it, of the metric space, which is uncountable and which is such that dxy is equal to 1 for every xy in x not equal. But dxy will be 0 otherwise if x is equal to y. So you manufacture an uncountable set such that the distance between any two of them is always 1. But at least we know that if you take any set of orthonormal vectors in a vector space, the distance between any two of them is 1. Okay? With any inner product and dot product. Actually it's enough. It is equal to k, some k greater than 0, fixed k. Normalize it to be always normalized. You can get hold of some fixed constant. Right. Okay. What do we get out of this? If we can manufacture one such a set, what do we get out of this? Now take any x in x. Take any x in and then choose epsilon to be 1/3. Okay? See what happens. If S is any dense set, B 1/3 x intersection S must be equal to non-empty. Okay? That means if we take x and draw a ball of radius 1/3, there must be a point of S. We'll call that point as Sx. Depending on x. There is a point of S inside. Now if we take another point y and draw a radius of 1/3 about it, these two will have nothing in common because the distance between the two is 1 and I have taken only 1/3 that side and 1/3 this side. Okay. So, this has to be arithmetically proved, but that's not the problem. Then there must be an Sy here of that set, yes. So what does that say? Corresponding to each vector in this set that you have manufactured, there must be one distinct element in the dense set. That means the dense set must have at least as many elements as this capital X has. But this capital X is uncountable and therefore that set must be uncountable. So therefore, for every X in X, we get Sx in S, and X not equal to Y implies Sx not equal to S. Therefore, X is equivalent to a subset of S. Because these are all, there may be other points in S, I don't know. And therefore, the cardinality of S is greater than or equal to cardinality of X, and therefore S is uncountable. So if any dense set will be forced to be uncountable. So if we can manufacture a set in such a way that every pair of them stay at a fixed distance from each other, all of them stay at the same constant fixed distance from each other, then any dense set must have at least as many elements as this manufactured set has, such a manufactured set has. And if you can manufacture that set to be uncountable, that forces the set S also to be uncountable. Now in the L infinity, we can manufacture such a set. So in L infinity, we can manufacture such a set. But what way we can identify it? It's not that we are cooking up a set or anything like that. We can really construct, we manufacture, and the construct maybe dictionary meaning may be the same, but concoct, that is a bad connotation. But really what we are saying is I can identify a subset of that L infinity which has this property. How do you identify this? Suppose I take the real numbers between 0 and 1. With each one of them, I can identify a unique binary representation. Okay. Only thing is again the problem with the terminating and non-terminating. You follow some convention. With each x, there is a unique. You use the right this thing, and then so for every alpha in 0, 1, there exists a unique binary representation A1, A2, or alpha 1, alpha 2, alpha 3, etc. Right? Now this gives me a sequence. Consider the sequence alpha 1, alpha 2, alpha 3. This is certainly bounded because the entries can be either 0 or 1, and therefore it belongs to N infinity R. So we will call it as alpha till. So with each alpha in 0, 1, I identify an element in the L infinity space. And what is the distance between if alpha hat is not equal to beta hat, at least one of the members of the binary representation, that the thing must be same. So one of them must be 0, other one must be 1. So the difference will become 1. So the maximum of the difference is either 0 or 1, so it has to become 1. So therefore, this will become 1. If alpha hat not equal. But this is the same as saying if alpha is not equal. So therefore, what we have got is, with each alpha, we have associated an element in L infinity, and therefore these alpha hats, if you take now all these alpha hats, they form an uncountable number of elements, and the distance between any two of them is 1, and that's what we want to manufacture. So let X be the collection of all such things. So therefore L infinity is not a separable space. It cannot have a dense countably infinite. The moment it is dense, it has to be uncountable. It cannot be. So that is the first non-trivial example of a non-separable space that you have seen. There can be non-separable space, there can be very simple, innocent looking non-separable spaces. Okay, like even simply take 0-1 sequences, obviously we see it's non-separable. So whenever you have a metric space in which there are fellows who are so much hate each other that they want to keep a definite distance pairwise, then that will have to have a problem if the number of fellows there are too many. If they are uncountable, then we have non-separable. Actually, the definition is that should be called separable. Because the fellows have been separated. This is, the other one is non-separable. They can be brought close to each other. Somehow or the other, the terminology is justified. Okay. So now I am going to make some more moves towards the some more examples towards this separable space. Now, all the classical examples of separable space, at least almost this very standard classical examples of the separable spaces. These are all so far examples of the discrete versions. Vectors with components, finite number, infinite number, and so on and so on. Next we will go to something connected with functions. Now we have not done anything about functions. We will have to talk about them, but everybody has some idea, somewhere or the other you have picked up. Whatever I say now, anything that is used will be proved later. It's very easy to say because after some time you will forget what I used here. Even if I don't know, it doesn't matter. It's like this, one of the most crucial steps in your theorem, you put it as a lemma and say that we will prove this lemma later, and then go on saying, suppose we had this lemma, the following is true, the following is true, the following is true, and hence my theorem is, either you forget to prove the lemma, or you say now the lemma is left as an exercise. You didn't know how to prove it, hopefully the examiner will prove it. Incidentally, it happened several years ago. One of my students, he was not my student, he was somebody else's student, and he wrote a thesis. He was an engineering department. He wrote a thesis which was very mathematical. It went to a professor, a very well-known mathematics professor at Brown University, Baron Kurosh. So by the time the thesis report came, the guide was away, gone, resigned and gone. So he asked me to temporarily look after this fellow until the thesis report comes and conduct the oral exam. I thought that was simply as a matter of administrative work. Then the report came, and this guy really grabbed this fellow's one big point in the thesis, saying that the lemma, the main theorem depends on the following lemma, number so and so, which is false. And luckily, he said, which is false. I give you a counter example. And he gave a counter example. And so I called this guy, look, I thought I'm going to write simply sign your papers, but now I got into difficulty. You have to settle this lemma now. So I asked this guy to look into it because I was not familiar. Then after some time he came back and said, I'm not able to settle the lemma. That means your thesis is questionable. So we sat down and looked at the lemma. Then finally we looked at his example. That gave us the clue. Why was his example a counter example? We started asking why that example worked against us. So therefore we want to remove those defects. See, that is the trend. You want to remove the defects. Then we found that we were over ambitious. We stated a very general lemma. A weaker lemma would have been enough. And that lemma, his counter example will not work. And then therefore we were convinced. Then we sat down and proved the lemma. If that fellow had not given a counter example, we would have been in soup. See, the way that person constructed the counter example, so clever. It gave us the clue as to what was wrong with our claim, and we could repair the damage. So sometimes it's advantageous to just send a lemma. You may not have a proof, but if the examiner is clever, he will object to it. And his objection will give you the clue to the right lemma. Don't try to do it in this thesis or something like that. It doesn't work always that way. Sometimes it works. You should be lucky if it goes well. Either you should be lucky if it goes to an examiner who doesn't realize that, or it goes to an examiner who is good enough to spend the time and find out what is wrong. In between fellows are difficult. Okay, so now we can go to, let me look at, again I have track of the following examples. Let us take the set of all continuous functions in, say, real values, continuous functions with the interval 0, defined. So what we mean is, we are looking at all these functions mapping 0, 1 to 1. There are some crucial properties of such functions which we will prove. Later, I can avoid it by redefining my function space conveniently, but we are going to prove certain property. Every such function is bounded. Any function which is continuous on a closed bounded interval will be bounded, and it will also attain its maximum and minimum. Okay, so that's known. Any such function of these properties we will prove that any such function will be bounded and it will have a maximum and a minimum. When I say a absolute maximum and absolute minimum, what do we mean by that? That is, what does one mean? There exists an m such that mod fx is less than or equal to m for every x in 0. The function is bounded. The values will not exceed m in absolute value. In other words, if you draw the graph of the function, speaking that if you draw, it should be limited within a certain band. 2. There exists a point x1 and there exists a point x2 such that fx1 is less than or equal to fx is less than or equal to fx2 for every x in 0. What does that mean? At the point x2 it attains the maximum. No value can be more than the value at the point x2 and no value can be lower than the value at the point x1. So at x1 it has the absolute minimum and x2 it has the absolute maximum. Absolute maximum does not mean maximum of the absolute value. Maximum of the absolute value. Absolute maximum means nobody beats him. That value above or beyond that. So that's what is meant by such a any continuous function has these properties. Okay. So now I am going to denote this space of functions by C01 and I will call it R because it is real value. Or some people put comma R. That not it, but anyway I will use this. CR01. This says the functions are defined on 0, 1. The values are real numbers. This C is continuous. There are continuous functions. Now we define a metric. So this is my omega. The collection of, so what are the points in the metric space? Each point is a function, or each point you can think as a curve, the graph of that function. So each point you can think of as a curve. So we are going to define the distance between two functions because the elements of the metric space are all functions. Now what we do is, you do something like the L infinity metric. When you had coordinates, we looked at the difference in the coordinates and then we looked at the maximum. Now exactly same way we look at the difference in the values of the two functions and that will be again a continuous function, therefore it will have a maximum, and look at that, maximum as x varies over 0. That is defined to be the distance between these two functions. Now you see that that is a metric, because it is always non-negative, because it's the maximum of non-negative quantities, clearly non-negative. When is it 0? If this has to be 0, maximum is 0. Maximum is 0, fx minus gx must be 0 for all x, which means fx must be equal to gx for all x, so the f and g are the same functions. So equal to 0, depend only if f equal to 0. Symmetric. If you put f and g in interchange position, the absolute value of minus g is an absolute of g value. And the triangle inequality follows, because triangle inequality follows for the absolute values and will carry over for the maximum. So that's very easy. So this is called the submetric or d infinity metric. So let's consider this metric space. Now our claim is this metric space is separable. There are lots of things that we will use for it, ideas we will use, all of which I will prove later, as I said. Now, if you look at our earlier attempt, always it boiled down, whenever you have this infinite situation, you somehow bring it to finite number of coordinates, others 0. And then try to approximate this finite number of coordinates by rational coordinates. It's essentially the same idea. Now, look at, for a moment think that our earlier fellows were almost right on their track. They said that we had the power laws, and then we have to build everything through the power laws. X squared, x cubed, x to the m. So they assume that we should be able to expand functions in powers of x, the power series. Okay? And let's assume for a moment, which is false, that suppose I can express a continuous function as a power series. If I had expressed it in a power series, the way to approximate it by finite things is, instead of infinite number of powers, take only finite number of powers, which is a polynomial. So the first question is, approximate f by a polynomial. Then the finite number of fellows have to approximate by rationals. So change the coefficients of the polynomial that you had into good rational numbers and you are done. And that's exactly what happens. Okay. So, idea 1. For every f in CR01 and for every epsilon positive, there is a polynomial f tilde, which is equal to a naught plus a1x, I don't know what order of the polynomial, such that any polynomial is a continuous function, right? Therefore, it is also in CR such that. Now, this is in CR01, this is in CR01, therefore I can talk about the distance between them. That is some less than epsilon. This is the result due to Bernstein. These are called Bernstein polynomials. Actually, we can write down what the polynomial. They have connection with probability theory also, but we'll come back when we discuss continuous functions. We'll look at that. So this is called the Bernstein polynomial. So given any continuous function, we can approximate it by a polynomial such that if you look at the difference between the function and the polynomial at any point, the difference will not exceed it. Maximum difference will also itself not exceed epsilon. That is idea 1. Next, even any f at polynomial this is easy because this is a polynomial, it can be identified with an n-component vector. Now this n-component vector can be approximated even by the maximum coordinate difference vector by rational, and then you construct the corresponding polynomial. So given any and any epsilon positive, there exists a polynomial f double theta whose coefficients are rational such that the maximum of the f hat f double hat. How do you do the approximation? Go through that. Take the coefficient, approximate them there, construct the rational this thing, and run the corresponding polynomial. And therefore, so conclusion, given any f in CR01, any epsilon positive, there exists f double hat, a polynomial with rational coefficients such that P epsilon f belongs to P epsilon. Okay? And therefore, these polynomials with rational coefficients form a dense set because they sit in any ball you construct around any point with any radius. There will be one polynomial with rational. And then there are only countably infinite number of polynomials with rational coefficients, and therefore it's a countably dense set. Okay? So, let me conclude it by writing that I want to use space. Set. Therefore, the polynomials with rational coefficients, set of all the rational coefficients form countable then set CR. Therefore, yeah.
There n is not a fixed number, that f hat is equal to.
That doesn't matter for me. I want to get an element of the polynomials with I don't say polynomial of that degree. Take all polynomials with rational coefficients. They form a countably dense set. They form a countable set. And give me any f in CGR. I will adjust the degree. I will adjust the coefficients but approximate it with epsilon. That's what I am saying. I am not saying n is a fixed degree. For some polynomial to get a better degree, I might have to take bigger this thing and so on. So I am taking the set of all polynomials with rational coefficients. It may be first degree, it may be second degree, it may be 100th degree. But it is a polynomial. That's I am not fixing a bound on the degrees of the polynomials.
Degree should be less than
I don't know. Then it's not a polynomial. I'm not calling it a polynomial anymore. Okay? A polynomial is an expression of that form for some finite n. Okay. Let me give you one more example. I got 2 minutes, 5 minutes time, so I'll just give you another example. This is B R T0. The collection of all functions mapping from 0, 1 to R, and B stands for not bounded, such that now I'm no longer asking for continuous, I'm looking only for bounded function. What happens? This is a part of that. The collection of continuous functions on 0, 1 forms a subset of the collection of all bounded functions. There may be bounded functions which are not continuous, but all continuous functions are bounded. So I am looking at a bigger collection of functions. So let us look at the collection of all functions which are bounded, and we define again the distance to be now what? If f is a bounded function, g is a bounded function, f minus g is a bounded function, and therefore fx minus gx will have a least upper bound. F is bounded, g is bounded, f minus g is bounded, so f minus g will have a least upper bound. So that is called the distance between f and g. Now let's take, for example, take this function 0, 1, let us take t equal to half and take the value 1 and 0 as well. This function we discussed last time. Take this function, let me call it as f. F of x is equal to 1 if x equal to half, 0 if x is not. This function is bounded. This is certainly not continuous. So there could be simple bounded functions which are not. Take another function g of x which is equal to 1 if x is equal to 1 by 3 and 0 if x is not equal. That is also a bounded function. What is the distance between these two? Look at the difference function. It will be 1 in absolute value. The absolute value will be 1 at half and also 1 at 1 by 3. The maximum will therefore be equal to 1. The maximum of the difference will be 1. The difference will be either 0 or 1 or minus 1. If you are taking the absolute value, the difference will be either 0 or 1, and therefore the maximum will be 1. So, what is that? So therefore, the distance between these two functions. Now you see that for every such point I can get one such function. Right? So for every alpha in 0, 1, we have a function f alpha defined as f alpha x is equal to 1 if x equal to alpha, 0 if x not equal to alpha. And f alpha, f beta, the distance is 1 if alpha is not equal to beta. Because this fellow is 1 where that fellow is 0, and that fellow is 1 where this fellow is 0. So difference will be always 1. So what does that mean? We already have how many functions of this type? For every alpha we have a function. And these are all different functions. Different alphas give me different functions. So there are as many functions as there are in real number. And therefore there are uncountably infinite number of such functions. They stay at a distance 1. Same trick. Therefore this space will be non-separable. Okay. So therefore let x be equal to this. Let x be equal to the set of all f alpha that we get from each alpha. Then x is an uncountable set and df alpha, df beta equal to 1 if alpha. Therefore, as in the case of L infinity, we get these are 0 or this non-separable. So what is happening is, inside this big non-separable space is sitting that separable space. This space of continuous functions is this that has the same metric, because when you restrict this metric for continuous functions, where is that? The supremum becomes maximum. No. Because the maximum is attained for continuous function. So when f and g are continuous function, least upper bound becomes actually the maximum, and therefore it is that metric only. So inside that huge big space of bounded functions, which was not separable, is sitting the space of continuous functions which is separable. So when you try to go from the polynomials to higher and higher levels, you are having certain properties retained up to some level, and then afterwards, because you are becoming more and more independent, some of these properties are lost. So you carry your genetic properties to some level, and then you start getting your own independent properties. Alright, so this now at least we have two examples of non-separable spaces, namely L infinity, little L infinity, and the space of all bounded functions. All other standard examples that we had, namely LPN, LP L infinity n, are all C01, they are all separable spaces. And exactly like I did before, I can take space of all continuous, real valued continuous functions are also complex valued continuous functions. Same ideas will go through. And similarly here, instead of taking a real valued bounded function, I can take complex valued bounded functions. They will form a separable space. Okay. So here we have therefore we have some now a number of examples of separable and non-separable spaces. Okay, I think I'll stop here. I will decide whether I'll start with I will decide whether I start with compactness or even to compactness I will take some small steps first and then reach compactness.